So let's get started. So essentially, what happened over the last three lectures, like we hopefully get a little bit of like glimpse of like the basic tools of continuous optimization, namely gradient descent method, and so how to analyze it, and then how to apply it in a concrete setting, namely the solving linear systems. And by this time, hopefully, especially if we read the notes, which has a bit more of explanation, you are fairly comfortable with sort of the most basic way to compute a maximum flow problem using continuous optimization. Okay, so remember that the way we thought about maximum flow is that we are trying to minimize over X that is the space of all the unit ST flows. What we are trying to do, well, originally we are trying to just minimize the L infinity norm. Okay, so just let me remind you. So f of ST is just the space of all the all the vectors that encode unit ST flow, which we by now know that essentially this corresponds to satisfying a condition that there is this matrix B, and all we want to do is that, like, if I multiply my vector times the this matrix B, what I will get demands and each vector. And I want these demands to follow a particular pattern, namely being 0 at every vertex corresponding to, well, vertex other than S and T, -1 at S, and +1 at T. Okay, so this is the basic formulation of max flow problem. So minimizing that will always give us an optimal solution. But then we realize that when we want to apply gradient descent to it, then we run into trouble. Okay, so one trouble is that actually this objective function is not differentiable. And also, even if it was differentiable, it doesn't have any good smoothness, okay, this beta smoothness parameter. Okay, so instead, what we did last time is introduce this proxy function as max of, well, in the end we set epsilon here of X, okay, with the same constraints, okay, and S max of epsilon of X was defined as log of sum over all the coordinates e to xi over epsilon plus e to minus xi over epsilon over 2m, when m is the number of different coordinates. Okay, and again, as I showed as an exercise, and I really would encourage you to do it just to get a feeling of what's going on, you can show that this thing is always upper bounded by the L infinity norm. And always lower bounded by L infinity norm minus epsilon natural log of 2m. Okay, so somehow, so this is our proxy, and the nice thing there is that if this is our in one dimension, if this is our L infinity function, which is absolute value function, then what softmax does, it somehow smoothens it, and somehow just takes care of this one corner and just like sort of distributes this kind of curvature on some more finite neighborhood. Okay. And once we do that, we know that actually S max of epsilon is 1 over epsilon smooth. Okay, which well, essentially now really enables us to apply gradient descent to it. Okay, so what's happening now is that now we have our algorithm in which max flow via a gradient descent. So what's happening there is that essentially we start with some initial solution, okay, and then what we do in each step is, again, it's always the same algorithm. Well, for I from 1 up to some capital T, what we do is that xi plus 1 becomes the old solution, and then we refine it by taking the gradient of the objective, right? So essentially here it will be, okay, so ideally it will be eta times the gradient of the objective at point xi, where our objective is just the softmax function. Okay, but like as we remember, we actually also care about this constraint here. Yes, like we also want to always maintain a solution in this feasible space, the space of unit ST flow. So just taking a gradient update might take us away. Actually, it's likely to take us away from the subspace. So what we need is also we need to project back on the space of feasible ST flow. So essentially, we need to compute, for a given vector y. What we get here is the arg mean over all vectors z of just the Euclidean distance between z and y, and z has to be in the space we care about. Okay, so essentially all of that the projection is doing is just telling us, give me back the closest point in L2 norm to the point that I just, that I just applied the projection on. Okay, so essentially this way, of course, I'm always guaranteed to make progress, like always guaranteed to get solution that, oh, sorry, actually this is wrong. So what we need is actually apply the projection to everything that we just get, not only to our update. So essentially we apply projection to everything. So we just take whatever is the improved point, but then we project it back on the feasible space. Okay, and at least in this way we always, progress in the feasible space, and as we showed last time, this actually does progress, and this ends up, converging to the optimal solution over time. Okay, and somehow the running time for us was to, what we can show is that essentially if we take the number of rounds to be roughly proportional to the smoothness times the initial distance to the optimum solution squared over epsilon, okay, then what will happen is that we will get a solution. So essentially if we take our solution that we got after capital T steps, its value will be, not larger than epsilon times the optimal value, essentially the value of the optimal solution. Okay, so essentially this, like all of this, is already a working, it's a working max flow algorithm. Essentially, that's you don't need to know anything about graphs, well, except to compute this projection. This really corresponds to electrical flows. And as we already last time showed, this corresponds in turn to solving linear system. And it's not only an arbitrary linear system, it's actually a very special system called, Laplacian linear system. So essentially, and we know how to solve it quickly. So essentially, like this solver, like this way to figure out, how to solve this linear system quickly is the only thing that really is about graphs. Everything else treats these things as just general linear algebraic objects. And somehow, you might not like it at first, but actually it turns out to be really, really, really important, because when you don't have to explicitly worry about like the paths, about like making sure that you keep satisfying flow conservation constraints. Actually, your space of possible things you can do broadens. Of course, in the end, it still reduces to something that makes sense for flows. But if you can have an abstract way of thinking about it that does not involve like having to think about it at every step of what you do, just via this projection, you have some generate translation. That's that's where your power and flexibility to get something better comes from. And now, of course, the question is: so this is what we can show, and now, what does it yield for a maximum flow problem? So we went over this last time. So essentially, we just have to look at these things and just like upper bound them the running time of the algorithm. So as we already mentioned, like as the softmax function has a smoothness of roughly 1 over epsilon. Okay, so one of these parameters is 1 over epsilon. Now, what can be this, like the initial distance to the optimum in L2 norm? Well, as we already said, so we know that the optimal solution, just puts on every edge a number between -1 and 1 because it has to satisfy the, well, essentially it's, it's something between -1 and 1. Okay, so in the worst case, it's essentially a path of length like omega of n in the graph from S to T. So, and then this, actually, even though this will not be strictly feasible, we can just assume that our initial solution is just all 0 vector, because then projection will project it back to the right place. So essentially, we can start it from here. So then we know that this is never bigger. No, this is essentially O of n. Okay, so essentially that no matter what this optimum solution is, it's never more than, like this L2 norm squared is never more than O of n from the initial solution. Okay. So, so far so good. So what is the running time? So the running time is essentially, well, this n over epsilon squared, because we have 1 epsilon coming from the smoothness. And of course, this is a number of iterations, but there, each iteration, it takes roughly near linear time to solve it. So we get this kind of, O tilde of mn over epsilon squared time, which, for sparse graphs is n squared over epsilon squared. And this is the state-of-the-art running time that we have here. Okay? So, if we compare to what we actually know about max flow, this is not too impressive. So, so the question now is, because we know that we can even compute max flow exactly in unit capacity graphs in, like for sparse graphs, this will be in n to the 3/2. Okay, so, and here we have O tilde of n squared over epsilon squared. So not only we have worse dependence on n, but also we actually have only solved the problem approximately, and we solve it only for undirected graphs. So essentially, so clearly, we are way behind the state of the art that was state of the art for the last 40 years. So, what are we even doing here? Like essentially, why are we even listening to me? Well, it turns out that again, this is what you get by fairly standard things, but very quickly, once you understand what is the problem you are trying to solve, you can get a more refined way of getting like a better version of gradient descent to solve this particular problem. Okay, and somehow the point of start here is how to come across the better method for solving max flow in this framework is that actually take a look at this thing, right? So essentially, like what was really the bottlenecking term in this whole running time was this initial distance to the optimum. Okay, and it's just very bad, like it's just very large. So essentially, the way things work, in particular, the way we are using L2 projections, we have to pay for it dearly. Okay, but then you realize that actually, like, why even L2, distance is the right distance to use here. Okay, so yes, it is the most natural notion of distance that we know, right? Like that's the thing we learn in the grade school, that essentially this is the distance when we think of a distance. But by now you realize that actually there are other ways of measuring distance, essentially using other norm. In particular, if you look back at the formulation of max flow, there is, there is some other norm, some other distance that seems to be actually much more natural for this problem, namely the L infinity distance. Okay, because in the end, if we think about it, when we think of the max flow and we want to compute a difference between like how much better quality a given solution is than the other solution, we just have to compare the distance in the L infinity norm, because the only thing that we really care is essentially how much, what is the worst case overflow if you want to sort of reroute one solution to the other solution. So it's really like L2 norm, as natural as it is, it's really not the right norm to use here. We should think about, trying to use a different geometry to talk about our problem, in particular L-infinity geometry. Okay, you know, but that's a nice intuition. But actually, how do you make it work? So you know, so how, like so far everything was L2 based. You know, why should we, like, how do we even change? Well, essentially, what we have to do now, once you have this key insight, is we just have to look at the derivation of what happened for gradient descent in the usual case. Yes. So essentially, the idea there was that if you are minimizing some function f with respect to like just let's say unconstrained minimization, then essentially all that we have to do is that essentially we looked at we wanted to get this local greedy improvement. Essentially, we would like to figure out what is the direction to locally improve your your function the most. And well, the way we got it is that if you essentially what we realized, you just realize that there is this kind of very nice way. So if I think of y as my next point to move, where delta is the displacement, then essentially there is this Taylor theorem that tells me roughly that I can just look at the value at the current point, then look at the first order correction, okay, and then essentially look at the tail, like the rest of these corrections. But in the end, essentially, for the nice function that we are considering, what we really care about is essentially the term that decays as as the norm of the delta squared. Okay, that somehow was the error term. So essentially, we wanted to minimize this, and we just wanted to, this gives us the direction in which we are moving, in which the delta should go, and now the extent of it, okay, the extent of it is exactly dependent on what is the interplay between the progress that we are guaranteed by the linear term that we are using to minimize versus the error and sort of the possibly counteracting increase coming from this tail that just comes from our our assumption that our function is locally linear. Okay, so in particular, when we talked about smoothness, then we essentially knew that I can just put beta over 2 here, and that this will be a good upper bound. And in this way, I knew that essentially, I just can clearly then the best direction to it was clear that the delta you want to move is essentially, it should be in the direction of the minus gradient, right? Because that's how we minimize this linear term the most efficiently. And then question was, how far do we move? And essentially, we figured out that if you just scale it by 1 over beta, then you are guaranteed that the term over here, whatever increase it comes from this quadratic term, the error term, it's actually not counteracting too much the progress from the linear term. And then we essentially got from that our progress. So essentially, if I look at the difference between what is the value function, so what is the value of the function at the at the beginning and then after taking step, which was this x minus 1 over beta delta fx, then essentially we showed that this progress that we made is at least 1 over 2 beta times the L2 norm of the gradient. Okay, so essentially, the larger the gradient, the more progress we make, and clearly we will stop when gradient becomes 0, and that will correspond, hopefully, for convex functions. This will correspond to a global minimum. Okay, so that's essentially like the whole analysis of, we have to of course do some we have to do something more to get convergence bound, but this was the basic principle of how we derived gradient descent and what is the intuition that why would you expect it to even work. Okay, but now again, all of that was done for for L2 norm, because again that was the norm we know. But now when you look at these expressions, they actually do not seem to depend too much on what is the norm that we are actually using. Because in the end, what we can think about is that, okay, so now we have again some function that we are minimizing. Okay, but then whenever we want to make progress, we might think of essentially, again, using Taylor expansion, but actually like this is no longer real Taylor expansion. What we just want is we just want to approximate locally the function. So again, this is x plus delta by, again, the value at the x plus the linear term. Okay. But then essentially what we would like to do, we would like to measure our error, okay, not in L2 norm, but in some other norm. Okay, so essentially now, yeah, I know that I was skipping writing 2's everywhere here, but now I actually would like this to be a general norm. It might not need to be the L2 norm. So essentially I'm just saying, okay, now the way, like the quantity I want to base my analysis on is the norm of the displacement, but not an L2 norm, just some different norm. Think about L infinity norm, for instance. Okay, so I just care for L infinity. I would just care about what is the largest coordinate of delta, and not essentially what is the total, like sum of the squares of this direction. Okay, so of course once I measure my my displacement in different norm, this beta over here becomes a different number. So for some functions it actually might now be unbounded. For some functions it might now become bounded even though it wasn't bounded before. So essentially now we have to generalize the notion. So essentially if you want to understand what is the beta that we should put here, which again beta depends on the function and on the norm we are using, then what we really would like to do is that we'll just define the smoothness again. So we say that f is beta smooth, but now with respect to the norm, some general norm. Well, essentially, the definition will be almost the same as before. So essentially, we look at the difference. Like so, we would like for any 2 points x and y, we would like to look at the difference of the gradients, and it should be at most beta times the difference of the points. So so for L2 norm, this was just exactly the definition of the smoothness. But actually, when you do the analysis of what the beta should be, then you realize that okay, here you indeed measure the distance between the points in the norm that whatever you want. But actually, when you measure the distance, like when you want to measure the change in the gradients, it's not this, you shouldn't use the same norm. What you should use instead is something called dual norm of this original norm. So essentially, so what is dual norm? So dual norm in general, so if I have some norm and I want to compute dual norm of it, then this is essentially corresponds to solving a minimization problem over all x such that the norm of x is at most 1 in the norm I'm measuring of the inner product x transpose times y. Okay, so at first this might not be clear why you have to do it. Okay, but it turns out that this is like if you want to get the constant over here, like if you want to know what is the constant over here, it will be exactly given you by this constant with this particular norm. Okay, you actually have to use the dual norm here. And by the way, just like a quick card, like if you have not seen it before, you should actually do this yourself. But you can so what you can show is that if your norm is the L2 norm, okay, then actually your dual norm is, well, it's also L2 norm. So essentially L2 is pretty interesting because it's self-dual, like it is the norm and it's dual of the norm, and that's exactly why in the original smoothness definition we didn't have the distinctions. We had the same norm on both sides because here the dual norm is the norm itself. But now for different norms, for instance for L infinity, does anyone know what is the dual norm of L infinity? So this is if you took like a class in functional analysis. That's something that is very important there. Sorry? L1, exactly. So it's L1. And now what is the dual norm of L1? Sorry? L infinity, yes, because things are always self-dual. If I take a dual, well, for reasonable norms, things are always like reflexive. That's what you say. So essentially, the dual of a dual is the original norm. Okay, so essentially that's it. And in general, for any LP norm, what you have is that essentially you get the LQ norm when the relationship is that 1 over P plus 1 over Q should be 1. Okay, so that's essentially the general thing for LP norms. And then the one more example of an interesting case of an norm to see what is the dual. So imagine I have an A norm. Like remember last time we talked about the A norm, which was defined as square root of n of x transpose A x. Okay, so this is the norm given by taking some PSD matrix A and just rescaling the norm by this. So then, well, the dual norm is actually very nice. Does anyone know what is the dual norm of that? Yes, exactly. So it is just, you just take the A norm, but with a inverse. Okay? And again, if I take A to be identity, it's just an L2 norm, and again we get like inverse of identity is also identity. So again, math makes sense, and in the end you are getting the same thing. Okay, but yeah, but the bottom line is that that in the end you still have this kind of you represent your function via this Taylor approximation. It's just now you measure your the sort of your displacement in different norm, and then this gives you a different constant here, but this constant exactly comes from this definition. And again, for Euclidean norm, everything just coincides with what we just talked about. Okay? So this is now the way we expand the function. Okay, so let me just rewrite it here. Okay, so now how do we use this Taylor expansion to actually get an algorithm? Well, again, the principle is exactly the same. We look at the linear term and we want to minimize it so much. We minimize it as much as possible. While essentially, so what happens is that we want to minimize this linear term as much as possible, but sort of our currency is how big delta is in the norm of our error. Okay, because essentially, if I have a couple of different deltas that have the same norm, then what I want to get the delta that gives me the biggest buck for the bank. Okay, so if I have to pay in delta having some particular norm, I want to just choose direction, choose the delta of the same norm that makes the most progress on minimizing the linear function. Okay, and essentially when you ask this kind of question, then essentially what would happen is that the best direction should correspond to essentially something called, okay, so essentially what you want to do is you want to look at direction which is actually minus, so ideally we would just like to what you would like to do is just move in the direction of minus gradient. Except now, what you will realize if you do the calculation is that actually if you measure your progress in L infinity, so essentially if you care about only L, the maximum coordinate of your vector delta, then actually just taking it, to be the minus gradient, you might be suboptimal. Okay, why is it so? Well, because somehow maybe essentially maybe this gradient has one big coordinate and a lot of small coordinates. And if you do the same for delta, then essentially, well, you are losing a little bit, because if you are measuring things in L infinity, you only pay for the largest coordinate. So you only make progress on one coordinate with essentially, if you pay for the largest coordinate, you might as well make sure that all your coordinates have exactly the same extent, right? Because you don't pay anything for taking more than essentially once the one coordinate is large. Might as well all the coordinates might be large. So essentially, there is clearly just taking the gradient itself is not the optimal choice. Okay, so what you really need to do is essentially you need to take the gradient direction, but then apply this sharp operation to it, which essentially corresponds for a vector. What this sharp is? Just let me make sure I get it right, so I don't mess up some conventions. Where is it? It's over here. It's essentially argmax okay, over all the possible directions u of, well, y transpose u minus 1/2 of the norm u. Okay, so what's happening here, we essentially just exactly try to like phrase directly this optimization problem in which, you know, I want to make progress on the linear term, so essentially I apply y to be exactly this, you know, this exactly captures, so this corresponds to this term, okay, but then I have this penalty. I want to penalize myself if I, you know, for taking too much movement in the direction, so essentially this corresponds to the second term. Okay, so this is measuring exactly the fact that if I have a couple of directions that have the same norm, I would like to choose the one that makes most progress on the inner product. Okay, so this is just an operation, and now again, if my norm is L2 norm, so essentially if I measure actually things in L2 norm, then this operator, if you do the computation, this operator is just identity. Essentially, it's always, you know, in this case, it's always better, like the best thing to do is just take the same vector and just, you know, and just apply it. But now for other norms, like essentially for L infinity norm, this is actually not so, because what you do then is essentially, well, you get a vector, so essentially its ith coordinate should be just the sine of y. Okay, and times the I think L1 norm of y. Okay, so essentially, so clearly, so what I'm just doing is I'm looking at the L1 norm of the vector y, and then since I have to pay for the, like essentially, here I just have this, sorry, the sign of the ith coordinate. So essentially, what I'm just doing, I'm just, you know, putting this sign in a way that in inner product I always decrease stuff, but then I, you know, just put the same value everywhere, because I pay for the largest value anyway, so I should as well just put all of it to be the same. Okay, so this is no longer you know, just the gradient itself. It will be just this kind of, I look at the sign of the coordinates of the gradient times the L1 norm of the gradient, and that's the best direction to use here. Okay, and you know, you can do exercises for trying for different norms, you know, what to do here. So in particular, just one norm I want to mention here is that the A norm. For A norm, actually you can show that the vector that you want to get is essentially A minus 1 over y. Okay? But yeah, but you can just play for L1 norm what it will be, and for any norm, you know, it makes some sense. Okay? But this is essentially all that we need, because now essentially we again have our algorithm. So this is like a general gradient descent. So what it does is, again, starts with some solution x0, and then the way the improvement happens is, you know, I take my old solution and I move in, you know, eta, the, well, not direction of the gradient itself, but direction of the gradient after applying the sharp operator. Okay, and that's the general gradient descent. And again, if you ask yourself what is the, at least from theory point of view, the best theta to put, you just put here 1 over beta, when, you know, again, the beta is this, the beta that we have over here. Okay, but essentially this is the algorithm that will work for, you know, for arbitrary norm, and sort of will take advantage of the fact that you care about some different norm than actually L2 norm. Okay, and somehow just one more thing is, so what happens when we have actually constraint optimization? So we actually want to optimize over some constraint set. Well, it's exactly the same principle. We just apply the projection after every step, but now projection, of course, is not an L2 projection. It has to be a projection that, you know, has the same definition but is in general norm. So essentially, I'm just looking, you know, the projection of y is just arg mean over x in whatever is my constraint set of, you know, all the difference in this, whatever is the norm I'm looking at. That, okay, so it's just the closest point in the norm that, you know, that I find. Okay, and And now the question is, okay, so what is the running time? Again, everything generalizes, you know, all the numbers are the same in the end, they just have a different meaning, a bit different meaning. So it's essentially now the running time is, you know, O of beta times the initial distance from the optimum, but again, the optimum in the measured in the norm that we care about over epsilon. Okay, and this is really the big gain. In particular for max flow, what you can show that for max flow, S max function is still 1 over epsilon smooth even in L infinity norm. Okay, so it was 1 over epsilon smooth in L2 norm, but actually it's also like 1 over epsilon smooth in L infinity norm. So you know, so here we don't lose anything, but the big gain is actually in, you know, the big gain is actually in the initial distance, because if I start from an old zero solution, and I know that the optimum solution does not flow more than 1 unit of flow on any particular thing, on any particular edge, then I know that this actually in L infinity norm, this is always at most 1. So we go from n to 1 by just choosing the right norm. Silly, right? It's essentially, it took us a while to figure it out, sadly. So now it looks like obvious thing in retrospect, but actually this took us a while. So essentially you get essentially like 1 over epsilon squared number of iterations for max flow. Okay, so essentially for max flow, we get from linear number of iterations to essentially 1 over epsilon squared iterations. Okay. Which is huge because, you know, essentially we have a, like, well, so we almost have a nonlinear time algorithm, except there is one piece missing here. Does anyone see what is the missing piece? So now we know that we are taking 1 over epsilon squared iterations, which is great, but what it is that we are missing still? Exactly. So, you know, one thing that I am actually like now it's hidden under the carpet is that, you know, but now you need to compute projection. So each iteration corresponds to computing this projection, which the projection now, you know, in infinity is just exactly computing, you know, the closest the closest unit value flow from whatever flow we just provide you with in L infinity norm. So we know how to solve this problem where here I have 2. Like when I have L2 norm, this corresponds to electrical flows. And, you know, we know how to solve it fast. But now we don't have L2 here, we have L infinity. And when you think what is the problem you have to solve to figure out this projection, then what is the problem that you end up with? It's the same problem, right? So this is, for L infinity, this is just maximum flow problem. So in particular, if I just want to compute the projection of a zero vector, that's exactly max flow of the graph. Like of the problem. So essentially, I cheated you. Okay, so in the end, yes, you have, like I told you, okay, you have just such a small number of iterations, but actually each iteration requires you to solve the problem exactly to begin with. Okay, so am I a charlatan? Did I cheat you? Well, I cheated you, but essentially for a good measure, because there is a way out of it. Actually, one of you asked about this earlier in the class. And, you know, that's a good instinct, because yes, if I want to compute this projection, it is really, I have to solve maximum flow problem exactly. But then you realize, do I actually need to solve this problem exactly? Okay, so, you know, how about just solve this problem alpha approximately. Okay, so I will not define it exactly because you have to be slightly careful what approximation means here. But as a first approximation, you just think of finding not the arg mean here, but essentially the flow that is within alpha times the minimum distance to the set. So essentially, you really just correspond. You just really want to solve. Well, essentially, again, there are some technical things, but in the end, you want to just solve alpha approximate max flow. So the question you want to do is not, I give you a graph computing max flow. What I'm just saying, I give you a graph computing max flow whose value is within like alpha, essentially it's you remember we are minimizing the maximum flows, the maximum flow on an edge. So essentially, I just want to get a solution that is within like alpha times f star for some alpha which might be much bigger than 1. Okay. In particular, I could think of alpha being, n to the little o of 1. Okay, so that's actually very huge. I'm actually like, let's say, logarithmic approximation to max flow. So the funny thing that happens is that when you use such an approximate projection as opposed to a real projection, you have to pay for it. Like that doesn't come at a price. So your running time goes from, previously it was this distance. That was the running time. Now what happens? You essentially have to pay alpha here. So the fact that essentially you only get alpha approximation projection, you have to sort of you don't make as much progress. You are always losing this factor of alpha in the amount of progress you make. But that's totally fine because even if alpha is like n to the little omega, this just adds just n to the little omega to my running time, and this is something I'm totally comfortable with. Because it's essentially like, I of course would be totally non-comfortable if my final solution was alpha approximate. But if I just need to take alpha more time, that's completely fine. And essentially that's where the power comes in. So essentially the moment I say, okay, instead of solving my problem exactly, it's like I want to solve my problem exactly, fast exactly, but actually instead I can just solve this problem, if I'm able to solve the problem approximately, and essentially I can bootstrap it to get the exact solution, that's sort of very powerful. And that's actually what, in a sense, all that continuous optimization is about. It's about just taking a difficult problem, like minimizing the function f, and reduce it to just approximately solving like simpler problems iteratively, and just using it to refine our solution. Okay? So essentially here, so that's the trick. So now the question is, okay, how fast can you solve, like if I just tell you, okay, you can use, like I just care about n to the little o of 1 approximation, how fast you can do it? Well, then essentially I showed at some point that you can really do it in linear time as well. Okay, if you just care about like polylog approximation or like n to the little o 1 approximation, and all of this together, so, all of this together indeed tells us that we have, still O of 1 over epsilon squared times now n times little o of 1 iterations. But each iteration takes roughly, well, n to 1 plus little o of 1 time. Okay, just to be precise. Okay, but that's okay. We have just like these two terms, but like they are, something we can totally handle. So we get a total running time of like 1 over epsilon squared times m. Okay, let's just be. This is the general running time. M like of essentially close to linear. Okay, solution, and this gives us like 1 plus epsilon approximate max flow. Okay, so suddenly things like went from very bad to very good very quickly once we realize that what it is that we want to achieve here. Okay, and this is how the fastest approximate max flow really works. And then you can actually like refine now we can play, and in the end you can even make it actually the current best result is like 1 over epsilon times m. But this is just refining stuff. But the basic idea is just this: that somehow you use the right geometry, which is L infinity, and then you use the fact that you don't have to like compute the projection exactly, because that's just a max flow problem itself, but actually you just can solve it approximately with quite a generous approximation bound, and you are still fine. Okay? So any questions about that? Everything is crystal clear. Yeah, Fedor, yes, clearly. Like, too simple for you, I know. Sorry to disappoint. So essentially, I just want to, so this is essentially all you really need to know about like solving approximate max flow fast. Of course, the question now is, okay, now when you can do approximate fast, how about the exact algorithms? Like how can actually getting exact? So I don't really have, I was hoping I will have time, but I don't really have time to go into that. So let me just tell you like a very, very, very high level, like 10 minutes overview of what's really happening. So essentially now, okay, so this gradient descent methods, like the way I told you is they actually are very nice, because they give you nonlinear time, but you have this polynomial dependence on 1 over epsilon. Okay, and this is horrible if you actually want to get like exact solution, because for exact solution, you need like epsilon to be something like 1 over n. That's essentially the regime after which you can, you can round the solution to an exact solution very fast. Okay. So by the way, just one interesting thing to know is that if I can reduce the exact directed max flow, okay, to exact undirected max flow. Okay, so essentially, directed versus undirected doesn't matter. So essentially, just it's okay to think about undirected max flow from the beginning. You don't have to even think about directed flow. But the important thing is that this reduction only works for exact things. So essentially, you have to be able to solve the undirected flow exactly, and not just one plus epsilon approximately for like 1 over epsilon squared dependence on in the running time. Okay, but the good thing is that you can think about undirected flow. So the only thing you really need to do is just get better accuracy. So okay, and essentially, so of course, once you know that's what you want to do, you can again look into the continuous optimization literature and learn. Okay, so what do people do when they actually want to get exact solution to a problem, and not this kind of 1 over like epsilon squared or 1 over poly 1 over epsilon kind of running times. And one powerful method that they do is something called interior point methods. Okay, so it's methods because there's actually many algorithms that have similar principle. The same way as gradient descent method is not one method, is actually a whole slew of methods. Okay, so what it is, you can think of it as just a way, to solve a linear program. Okay, just exactly. Okay, so this will be again like just a crash course just to give you the keywords, but like this probably will not be too insightful in the end. So what is an LP? So I can just think of any LP as just a minimization question. When I minimize minimize x, there is some objective function that is linear, and I have constraints which, for instance, I can just assume are of the form let's say negativity, non-negativity, well, not non-negativity, but essentially like I'm just saying, I have these inequalities going one way. Okay, for some matrix A and some vector B. Okay, so I would like to solve this problem with inequalities. So how do I solve this problem? Well, essentially, a priori, it's actually like optimizing over inequalities is difficult because the projections are actually difficult. Okay, so essentially, it's not an affine subspace as it was before. This is actually like some kind of polytope. And projection on this actually is very difficult. It essentially corresponds to linear programming itself. So how do we approach this question? We still would like to use it like continuous optimization methods to solve this question. So what we do instead is essentially we sort of we want to nix these non-negativity constraints and enforce them in some implicit way. So how do we do it? So we essentially, take our original LP, and we define a certain perturbed version of this LP. So what we do is we want to solve a problem in which we just like look at unconstrained minimization. So x can be whatever, and then of course we want to minimize the objective, but now we have to account for the constraints. So what we do, we introduce something called a barrier term. Okay, so it's mu. So mu is just a scalar, like it's just something that is strictly positive. And it is. I just have for every constraint, I just look at the log of. I think I might not writing it. So I look at the essentially. I look at the jth inequality. Okay, and I just take a log of it. Okay, so what is the idea here? The idea here is that if I look at the log function, or actually minus log function, then how does it look like? So essentially, what happens is that, well, it looks like something like that. Does it look like that? No, sorry, that's not the right function. So it looks like something like that. Okay, and the point is, and that actually there's only one thing that we care about really here for the moment, is the fact that as we see, as we try to approach, like if we are somewhere here, and as we try to approach the we try to transition into negative numbers, these things explodes to infinity. So essentially, since we are solving a minimization question, the fact that we will get penalized the closer we get to even to this negative ortant, then essentially we will be repelled from ever crossing there. So essentially, as long as mu is positive and we start from a solution that has all of these things satisfied, then essentially as we will minimize stuff, we will never actually violate any of the constraints. Okay, because this will just always repel us away from doing that. Okay, so we have taken care of this non-negativity constraints. Well, not negative, like this inequalities by just introducing this. This is called the barrier term. And of course, a priori, I could use different functions. Like this is a convenient function for some reasons that I will not tell you why today. But I could use anything that explodes to to infinity whenever I try to escape, leave the feasible space. So that's great. But that's great. I have barrier term, so I always will get a feasible solution. Of course, the problem is that now the problem I'm solving is not the problem I wanted to solve. Okay, because clearly now I'm minimizing something different. I'm not minimizing, I'm not minimizing just the cost, but I'm minimizing the cost plus this barrier term. But still, so two things that one of them you have to trust me is that essentially the nice thing is that for mu sufficiently large, okay, so let me, essentially I can get the optimal solution. So let x star mu be essentially the optimal solution to this like the problem LP mu. Okay, so essentially for mu sufficiently large, I can find x star mu easily. Okay, so you can just assume that if I make this perturbation large enough, essentially if I make it so large that it completely overwhelms this linear objective term, then essentially I forget about objective values, and actually there is a way. Let's assume that you can just do it, you can get the solution easily. But now, of course, it's not the solution you are looking for. So the other thing that you can still notice is that essentially as I look at the limit of mu, no, sorry, my mu writing skills degraded. Essentially, if I look at mu in the limit of going to 0 but staying still positive, then essentially if I look at the solutions I'm getting, then they in the end will approach the solution I'm looking for. Okay, so essentially, like if I take mu sufficiently small, I can be sufficient, like, you know, for increasingly smaller mu's, I get increasingly closer to the actual solution I want to compute. Okay, and this actually gives me an idea for an algorithm. So this is like called path following algorithm, in which, you know, what I do, I start with x star mu for large mu. And then what I do is that I just repeatedly refine it. So essentially, I use a x star mu for some value of mu. And what I want to get from it is x star, x star mu prime, where mu prime is 1 minus delta, the old mu. Okay, so essentially what I want to do is I want to just, you know, start with some solution, then based on that get a solution for a slightly smaller value of mu, then again and again and again until the mu is sufficiently small that I'm actually happy with it. Okay, so well, there is many questions here that I did not cover. In particular, how do you use one solution to get the other solution? And the answer to this is something called Newton's method, which I did not have time to cover, but you know, that's essentially something that's essentially the idea in Newton's method is that instead of looking only at the linear term of the function, you actually look at the quadratic term of the function as well, and then you deal with this kind of, you know, higher order error. Okay, so sort of like this is a more powerful version of gradient descent, and you use that to minimization. And again, just to tell you very quickly, like the very interesting thing about Newton's method is that as long as you are guaranteed to start from a point that is sufficiently close to the optimum, your convergence is extremely fast. Like it's actually like double logarithmic in 1 over epsilon. So essentially, so the point is that as long as, you know, the new mu is close enough to the old mu, then you have this guarantee that, you know, you are in this radius of rapid convergence. So actually, like this, you know, this computation is actually very fast. Okay, and essentially, like that's how you always use Newton's method in its regime of rapid convergence, and this allows you to make a lot of progress. But again, this doesn't probably make much sense if you have not seen Newton's method before. But now the last thing I just want to say is that actually, so I call this thing a path following algorithm. Why? Well, because there is a very nice geometric picture that also explains the name of the methods. Yes, like the name is interior point method. Okay, so what's really happening is that if I look at my feasible space, okay, so this is the polytope over which I am optimizing. Okay, and let's say my cost vector goes in this direction. So it means that, well, I know that the optimum solution is in the corner of this corner of this polytope. So what's really interior point method is doing, so it starts with a solution for like mu being very large, and this corresponds to something called analytic center. So analytic center of this polytope. Okay, but now if I look at all the solutions, like as I vary mu from, you know, from infinity to essentially 0, then I will, for every mu, I get a solution, like I get a feasible solution to the corresponding LP mu. So I can actually, you can show that this actually is a curve that is parameterized by mu. And what this curve is doing, it's starting at the analytic center, and as mu goes smaller, it actually converges to the optimum solution. Okay, so essentially, so this is like in terms of like just, you know, mu varying continuously. You have this path. This is usually called central path. Oh, sorry. Okay, and it exactly leads us from somewhere where we know how to get, namely from here, to all the way where we want to get, which is here. Okay, and in particular, this explains you why this interior point method, because we are in the interior polytope, and we sort of like go from inside all the way to the boundary to the optimal solution. Okay, this is in context in contrast to simplex, which always works on the boundary. So here we just go from within, and actually again, this is actually, so simplex is very combinatorial because we have to pivot in constraints and pivot out, and this is very complicated to analyze. Here we forget about constraints, we just like abstract away, we just are inside, we just sort of sense them only through the barrier function, like just, you know, because the barrier function makes sure that each of these things repels us. But, you know, based on that, we are just like sort of slowly zooming in on the solution and just hitting it, you know, from inside. Okay? So, and all that we are doing with our algorithm, of course, this is a continuous process. So what we are really doing, we are essentially looking at the discretization of following this path. So essentially we start with something, we take a step, then, you know, like essentially we are just trying to find, you know, a discrete approximation of this path and, you know, converge to all the way to the optimum solution. And then you can ask yourself, okay, what is the running time? So in particular, what is the number of iterations needed to get epsilon approximate solution? And the answer is essentially square root of m times log 1 over epsilon. Sorry. Okay, so it's log 1 over epsilon, which is great. What is not so great is this square root of m, because even though you can show that for max flow you can implement each iteration in linear time, this just gives you, you know, O tilde of m to the 3/2 log 1 over epsilon, which actually matches the state of the art and gives you exact algorithm, but again, somehow we wanted to improve. So then in some work, but this is like a long-standing upper bound, and what I show that essentially in my work that you can get something better, at least for max flow, and its unit capacity max flow. So this is the only moment when actually what we know for unit capacity is better than what we know for general capacities. But essentially, like, you can improve this iteration bound, and this leads to a faster algorithm of m to the 10�7th, which essentially, and then exact. Like, once you have log 1 over epsilon, you can essentially get it exact. Okay, and that's how the fastest exact unit capacity algorithm works. Okay, so I think that's definitely, you know, enough to say in this kind of, you know, 4 lectures. I hope it was like, I hope you got some feeling out of it. So again, I don't expect you to just be ready to just jump in and do this yourself. I encourage you to actually try. But yeah, but this is the thing that you really have to compute things yourself. You have to, you know, things are confusing again, then you have to read up and like, you know, this is just a new way of thinking about optimization and new to us. Of course, this field is very old, and, you know, there are people like Nestorov who invented it and thought about it. So to them, this is the obvious way to think about it. But I think, you know, to our community, this is definitely somewhat foreign. And, you know, theory is about connecting ideas, and this is definitely a new host of ideas that we can connect to the things we know. Okay, and out of this, I think there are already some beautiful algorithms coming from, but there is like way much more to do. So, you know, hopefully some of you will actually, you know, descend to this quest. Okay, thanks.